So here, right, just we are going to focus with instruction level parallelisms. So here, chapter 3 is all about instruction level parallelisms. So, and I told you, right, when you want to achieve instruction level parallelisms, it can be done by two ways. One is by means of a software or else by means of a hardware. So when it is software, it is by means of compiler. We can do it with respect to compiler. Hardware means we can define, in the hardware itself, we have that opportunity to go with the instruction level parallelisms. So in general, right, so this we have discussed. So with respect to pipeline, normally, right, the CPI will be ideal pipeline CPI. It will be there always. And apart from that, we have few stalls. So these stalls, I told you, this may be because of three reasons. So one, it may be a structural. The other one may be your data, and the third one may be control hazards. So when you talk as structural, so if you're just going with respect to structural, so this is because of resources. So because of resources, you may have a stall. So what do you mean by stall? I mean, it's we don't have any input, and the processor it won't do anything. So appropriate because of something, it is going to wait it. So that's where staying is the stall. So here the stall, it's that can be with respect to these three things. One is structural, data, and the control. So first structural. So if we take our pipeline, okay, let it be. So because thereafter we are going to explain with respect to pipelining all those things. So normally, right, this MIPS is a 5-stage pipeline. We have a fetch, decode, execute, memory, and write back. Okay, so keep remember about this 5-stage pipelining. Okay, assume this. So this memory part will comes into picture whenever your if you have a load or store instruction is there. Okay. Clear. So if suppose if you have a load or store instructions, this part will get into picture. And similarly, right, this write back is here only, right, we will write it to the registers part. Yeah. So this what you have these stages. So fetch, decode, execute, and the cases. So coming to this part, structural part. Suppose we have an instruction one. So okay. So instruction one will be there in the first stage. So when you go with this instruction two, instruction three will be here. Sorry, instruction one, instruction three, instruction two, instruction one, then four, three, two. Again, that we have an instruction 5. We have this instruction 4, 3, 2, 1. Let it go. So this is, this what it will be like. Suppose if it is a pipelining cases, so it may be like this. Assume that you will take a memory. Okay, so you have this process. Okay, so this instruction is the, assume instruction 1 is the load instructions. So when instruction 1 is load, so what will happen? Instruction 1, when it is load or store instruction, probably, right, it may going to take a value or it may going to store the value at this 4th clock cycle. At the same time, what will happen here? What is happening here? So what is this? Here, what happening at instruction 5?
Fetching.
It is fetching. Where it needs to fetch?
Instruction memory.
Yeah, instruction. It needs to fetch the instruction from memory only, isn't it? Understood or not? Okay. Because in the memory only somewhere, right, you have some instructions will be there and your data will be residing. But whatever the data transfer is happens, all will be happens with the help of this port only. So in this case, what is happening? this fourth clock cycle, this case, instruction 1, it just come here, sorry, this place, okay, not 5. So when the instruction 1 is trying to write, load or store something data onto that, at the same time, right, instruction 4 is about to fetch the data from the memory. So what will happen? So both is trying to access the same resource. Okay, so here right, both has been trying to access the same resource. So in this case, what will happen? So probably right, you may have a stall, because what is that resource? Both is trying to access the resource memory. Since it is a uniform, only one can be at a time, one thing can be transferred. So it may leads to a stall. So normally this is the things I told you. It cannot be done programmatically. When you just go with the structural results, it cannot be carried out normally. But the solution one, the best solution is one is you need to wait it, and then we have to proceed. On the second stage, what we need to do is we need to duplicate. We need to duplicate the hardware parts. So this is what we can do. Understood. So this what we can do it with respect to the structural hazards. So keep remember the structural hazard will occur because of the resource conflict. Whenever I two or more instructions or whatever it is, it may be anything. So when try to access the same resources, so probably there may be a stalls. Okay, this is with respect to structural hazards. So the next thing is. Sorry. The next thing is data. So like your syllabus, like we are going to focus more on these data hazards and data stalls and the controls, only these two things. So nothing with respect to structure, but in general, right, you remember, right, structure is occurring because of the resources. So that can be either we have to wait and it has to get solved, or else, right, we can duplicate the processor. That's the thing. Okay. So in the next one, we'll just go for the data hazards. So as we are just speaking about the instruction level parallelisms, so almost right, it is all about we are going to exploit the parallelisms in the instructions. So it is not between the task or those things. We are trying to establish the parallelism in the instructions. So on the day I told you, so what is basic blocks? Okay, class done up. So what is basic block?
Code sequence with no
Okay,
branches.
just it's just a straight line of code, isn't it? So it's a straight line of code. So we have set of codes. So which means between this, assume that this is a block one. So within this, there won't be any branch. Maybe at the entry or at the exit part, you may have a branch, but in these cases, you don't have a branch. So like this, right? Wherever you have a branch, so they will divide it into it will be divided into basic blocks. If you have a branch statement at this point, let it be branch equal. So with that, you may have one block. So after that, right, it may be either this or this. So like this, the basic blocks will be there. The thing is, if you want to establish a parallelism within the basic blocks, it may be easy. Why so is, I think there is a survey. What the survey says is, between 3 and 6 instructions, between every 3 and 6 instructions, you may have a branches. So when you have a branches, assume that in this block only 3 instructions, like instruction 1, instruction 2, instruction 3 will be there. So instruction 4 will be the branch. So, in this case, if there is any dependencies, it can be easily solvable. The number of instructions within the basic class is going to be less. Parallelly exploiting the parallelisms in one or other way, it may be easier. But normally, right, as this restriction is there, so if exploiting parallelism between the blocks may improve the performance. So we need to, the important thing is, right, so exploit the parallelisms among multiple blocks. That is very important. So that way what will happen? The performance will be enhanced. Clear? So, I mean, this is the base things. So here, right, our motivation is just we are going for instruction level parallelisms. So first, right, we will see an example wherein, right, if you want to exploit the instruction level parallelisms, it can be done in loop level parallelisms. So, I mean, in case of loop level, so we can try to achieve this instruction level parallelisms. So on the day, right, I wrote a code. So, for example, if you have a C code for I equal to 0, like I less than or equal to 99, like I plus plus. So, x of I equal to, x of I plus y of I. So, this is the code. Now, right, first we will write the equivalent mix code. I told you on the day, just keep remember like this. So if you take these instructions, right, they're going for the floating point operations. So first, right, they are just loading for x of I. Okay, let it be. This may be a scalar value. So instead of y, right, it may be a some scalar value. So if that is the case, so what will happen? Keep remember this. So just we are just loading f naught from some location. Okay, so keep remember, let it be. So if this is the memory location, you yourself fix it up. So initial element is at this place and last element is in this place, which is pointed by R of R2. Okay, this one. So what we will do, so we will fetch it and we will decrement and we will keep come like this and finally we will reach. So that way, right, we will compare if R1 is equal to R2. So probably, right, 8 of R2. So if it is equal, it may be the case. So you think, generally, right, this is the maximum, the topmost value that is stored in R1. Until how many elements you need to fetch? So those many elements, and that last index has to be there in the R2. So, this is what the assumption is made. So first, right, we are trying to load this xi. So once we load it, so what we are doing it is double. Okay, we are adding it with a scalar value. So that scalar value is some constant. Okay, that s is there in the f2. So after that, right, we are just storing the result to the same locations. Now d add ui. Okay, so d here is a decimal unsigned integer. So we are just decrementing the R1 for immediate. Okay. So here we are given an immediate data. So directly we are decrementing. So if it is not equal, if R1 is not equal to R2, so again, right, we need to go for a loop. So this is the looping statement. Okay. So hope this instructions may be clear to you. So now, right, we will try to explore like what are all the possible dependence that is available in this code. So on the day itself we have discussed. So when you just go with the dependence aspects, majorly, right, two major cases. One is data dependence. The other one is the control dependence. Okay. So in general, right, maybe a few classifications, but if we just go with the two cases, one is the data dependence case. The next one is the control dependence. Okay. So first, right, we will go for data dependence. In case of data dependence, if just for an example aspects, we will take like this. You have something like add. See, when you are writing the mnemonics, then try to, it should be in capital. Okay. So add R0, R2, R3. I mean, don't think that it may be like since you are writing it, you can write it casually, but just have as a practice. Any mnemonic, any opcode, I mean, you try to write it in these things, capital letter as a practice. Okay. So we are adding it. Assume that subtract R4 comma R1 comma R4. So then maybe anything you can let it be. We just try to do an AND operations. So maybe we have like this. So when you take these cases, suppose if you try to analyze this case, so what is happening in case of pipelining? So pipeline is what? Fetch, decode, execute, memory, and the write back. Clear? So this write back, here only write your registers will be available. Clear? So now the thing is, right, so when the instruction 1, assume when the this is instruction 1. So when the instruction 1 is in execute stage, I mean this here it goes. So you will go in this order. So instruction 2, instruction 1. I think, I mean, this what, I mean, it will be like this, right? So instruction I plus 1, I plus 2, I plus 3, and then right, it is I plus 4. You have this. So what happened is, at this stage, let it be. Here, when instruction 2, this, if you check instruction 2, instruction 2 is what? Depending on R1. Similarly, instruction 3 is also depending on R1. Okay, so this, when instruction 2 is in execution stage, what it needs R1. But when R1 comes, only at this stage, right? You got it?
Right back.
Yes, yeah, only at write back. Clear? So only at once it write back to the registers, then only right it can able to execute. Because when it goes for an execution, it should need both the operand. Then only right the ALU unit can able to execute. So this part clear. Since at this stage only we will get the R1. So here right, it cannot able to execute. So probably right, what will happen here? Will it execute? Will this instruction execute?
No, ma'am.
So there may be a I have written just like that, but normally, right? So since that is a dependent, okay, so I2, I mean, since it has to be depend on the value that I1 is going to write, so probably, right, you may have a start. So this part they are saying it as a data dependence. Clear what is data dependence? Clear or not? So this, so the previous case also, here, right, what is the data dependencies? How many data dependencies are there? You may get a question like this. So they may give some set of instructions and they ask you to find out the data dependence. So you must be in a position to find out that. So when it is a data dependence, it is clearly a true data dependence. What I'm explaining, this is a true data dependence. Okay. So can you say what are all the true data dependencies here?
F0 and F4, ma'am.
Okay, this part, right?
Yes, ma'am.
In these two instructions, because this F0 is going to be used by this, so probably right you may have this, and this F4 is going to be used by these instructions. You may have a data dependence. How about this instruction? R1 is decremented. After that only it has to be used. So all those three are data dependence instructions. Understood or not? So what something you need to do it, some rescheduling or something has to be done, and accordingly we need to take it. We'll see like what are all the methodology to avoid this data dependence later, but just first you be clear what is data dependence, true data dependence. So is there any doubt in this true data dependence? So it is very clear. So the simple statement, so suppose instruction I is produces a result that may be used by instruction J. So assume this is instruction I, so this is J. So whatever the result that is produced by I, if it is used, it is going to be used by J. So probably right, you may arrive a data dependence. Clear? So that we are saying it as true data dependence. The next one, okay, this is true data dependence. The meaning, what is the hazards that is name associated with this true data dependence? So they are saying it as normally, right? They will classify dependencies as data and control dependencies. Okay. So with respect to dependencies, it is as okay, two types, and with respect to hazards, so we have three types. One is RAW, another one is WAR, WAR and WAR. So what is this? RAW is read after write. WAR is write after read. WAR is write after write. Okay. So with respect to data dependence, generally, okay. So we have these three hazards. So first, right, we are just seeing about the true data dependence. So what is the data hazards that have been associated with true data dependence, which is RAW. So what is RAW? I told you. So instruction J reads, tries to read a source before I writes it. Okay. So in these cases, so let it be. If suppose before executing this instruction, if J write it, if it executes, suppose if it executes, what will happen? What happened?
Long.
So something right, because we don't know. It may be some older value will be there in that. You understood or not? Clear. So this what they are saying is that is the read after write. So once it is written, then only right we have to go for read. So this hazards it is called a true data dependence. Clear. So whenever right you have a true data dependence, suppose if you are trying to reorder the program, we need to ensure it properly whether it has done. I mean, our read after write happens. Simply, we cannot reorder this program. So this has to be done properly. Okay. So this is about RAW. Okay. So true dependence. Whenever you have a true data dependence, the associated hazard is RAW. Read after write. Clear. The next one is again with respect to data dependence. So one more category is name dependence. Under this name dependence, two categories we have. One is anti-dependence. Another one is output dependence. Anti-dependence and the output dependence. And which hazards has been associated with these things? So with respect to anti-dependence, it is war, and with respect to output dependence, it is going to be war. So we will see what is anti-dependence. We'll go with one example. Suppose assume that we have an instruction like this: subtract R4, R1, R3. Okay. So, I mean, you just go with the, okay, leave about these instructions. You just compare between I and J. So, what is happening between I and J? It is a sub R4, R1, R3, and R1, R2, R3. So, here, what is happening?
Two different answers are being stored in R3.
Okay.
Subtraction and addition.
Subtraction? Okay, listen. If suppose if I'm trying to do this, I mean, I'm trying to execute J before subtractions. What will happen? Will it be right?
Wrong, ma'am.
Right. So if you take a var, that is right after read. It should be, I mean, this case, right? When it has to write, only after it is read, it has to be written, right? You got it or not? So suppose if add is happened before subtraction, whatever add does, that R1 value will be here. Suppose assume that initially R1 value is like 0.8. So this may supposed to use 0.8. Suppose after adding this, maybe R1 value may result at assume 10. If this happens before, so probably right R1, there is a possibility to get the R1 value as 10. So definitely right, this is going to be the wrong answers. So you will get an incorrect answer. So this what they're saying it as var hazards, which means instruction J tries to write a destination before it is read by I. Got it or not? So R1, right? Instruction I is going to read R1. Okay, instruction I is going to read R1, but the same register is going to be used to write by the instruction J. So this is called anti-dependence. So you will see how to solve this problem. Next, you will go for output dependence, and then I mean we will give a common solution for both. The next case is output dependence. In case of output dependence, so what is that hazards it has been associated with? It is the wow hazards. So if you have this, subtract R1, R4, R3, something, and R1, R2, R3. So you have like this. So I mean, this is I instruction, this is J instruction, and this is the K instructions. So this case, so what will happen is, suppose right, according to these, I mean, flow of the program, whatever the output that is produced by R1, that is going to be used by the K instruction, right? I mean, this what is this dependence? What this dependence is? This and this.
Data dependence.
Data dependence, right? The output of this instruction is going to be used as an input for the next instruction. So clearly it is going to be a data dependence. Suppose, assume that I'm going for swapping. So J executes first followed by I. So this is what output dependence. So J, I'm writing here, J tries to write an operand before it is written by I. Okay. So this one, J, right, it is trying to write to the operand R1 before I writes. So if it happens, so probably, right, so what will happen? This, what R1 will get? If J1 writes before, so R1, right, it may get the result of sub, but actually what needs? Actually it needs the output of add.
Add.
Here. So, so that also right. it may be a problem just when you are trying to order the program. So with respect to this name dependence, what might be the solution? Will there be any solution may be there? Is there any dependence between this sub and add?
No, ma'am.
Dependence. What is the case? What tries to prevent to make it parallelisms? Only because of R1, right? Since it is also using R1, this is also using R1, so you may get a problem here. So what we can do is, so instead of R1, let it be. Can I make it this as R8? If I make it as R8, will that be any problem?
No, ma'am.
No, ma'am.
Problem, isn't it? Similarly, right, I'm just storing the value. Instead of R1, should I, if suppose if I'm using it as R7, will it be a problem?
No, ma'am. Yeah.
I mean, see, parallelly those things has to be reflected here also. I mean, this has to be reflected to R7. When I'm just trying to change this as R7, so here, right, I'm making it this as R8. So parallelly, right, this should also be changed to R8. Okay, so that has to be taken care. I'm just dealing with this I and J instruction only. So if I'm just trying, if I'm what actually trying to do here? What is the solution I'm providing for name dependence?
Changing the name of that.
Temporary register.
Yes. So what is the solution I'm providing here?
Adding new registers.
Yeah, simply right. I'm giving register renaming, isn't it? So this case, right, instead of R1, right, I'm just going for R8. So I mean, in this case, right, instead of R1, again, right, I'm just make it as R some, whatever it is. You understood or not? So the solution to the name dependence is register renaming. So there is no data dependence. Only with the respect to the name, we are getting that conflict. So what the only solution is, we need to go for register renaming. But in case of true data dependence, we cannot go like renaming. Because it is completely dependent. Only after executing, only we can able to get the values. So probably we cannot go for register renaming. If we go for renaming, it may result in wrong output. Understood or not? So it has to be taken care in different way. But with respect to name dependence, so keep remember with respect to name dependence. So data, or else you make it two way. So data dependence as one is a true data dependence. Another one is data dependence. Okay, so true data dependence, we have to provide some way to do it. But when you just go with the remaining two cases, what is that? One is anti-dependence and output dependence. By register renaming, hope we can able to solve these things. Understood or not? Clear?
Yes, ma'am.
Till this any doubt? If you have any doubt, you can ask me. Data dependence. So in general, keep remember data dependence, two types. One is true data dependence, another one is name dependence. So when it is true data dependence, so reordering, you have to be very careful. So output of instruction I is going to be used by instruction J. And with respect to name dependence, two things. One is anti-dependence, another one is the output dependence. So anti-dependence. So anti-dependence, J tries to write a destination before it is read by I. So the hazards that have been associated is what? Write after read. The next one is output dependence, and the hazard that is associated with output is wow. Write after write, and for true dependence it is RAW. So I can damn sure I can say right. Definitely you may get 2 marks on this spot. Either they may ask you to give an example of this, or sometimes right they may give a program and they ask you to identify like what are all the dependencies that are available, or what indirectly, I mean, either they may ask you like what are all the dependencies available, or what are all the hazards that are available between the instructions. So you must be very clear in differentiating all those things. Okay, shall I go to the next control dependence? See, if you have a doubt, then and there, just stop it and ask. How many students are there? Only 36. See, it is not like, I mean, though the book is like theory, it is not like a theory. So, I mean, like inform your friends just to attend that class. Because only by attending the class, so we can able to. Okay. Okay. So only by attending, right, you can able to solve the problems. Definitely, right. Only problem-based questions you may get it. So again, I repeating, just inform your friends to come to the classes. Because like within a week, 36 members are there, so it's too bad. So take care of it. Okay. So the next one is the control dependence. So when you go with the control dependence, so purely right, it is associated with respect to the branch instructions. Okay. So you have a this one, right? So control dependence is associated with the branch instructions. So generally, right, there are two constraints which have been imposed by control dependence. Okay. So what is that two constraint? The first one is suppose if I have an instruction, so that instruction is control dependent on a branch, cannot be moved before the branch. It is something like this. Suppose I have an instruction like this. So in this case, I have an instruction I3. Normally, what will happen? If the condition is evaluated, so right, assume if it is going to be true, this part will be executed, or else right, then part will be executed. You know this rule. Can I take any one statement in this and can I put it over here? Can I do like this? Is it correct? Any instructions I can take out of the branch, that means the set of instruction that is controlled by the branch, in that I'm just taking an instruction. If I'm placing before the right, is it right?
No, ma'am.
It's not right. Is it correct, right? So we cannot do it, right? So see, why these problems and all? As a what to say, like an end user, when you are writing a programmer, we are not worrying about. I think so. You may think, oh, it's a stupid thing, right? Why some instruction is inside if, why we are going to take outside and we are going to write? So we are not going to do it. I mean, right? When the compiler is going to write, it will check all those things. Okay. So because it needs to go for an optimization. So when it is tried to do an optimization, if something is bring out of the loop, because some program scheduling will be done, instruction scheduling is going to be happens because it needs to achieve a maximum performance. So for that, right, whatever the instructions we are going to given, whatever we are written in high level languages, it is going to be converted to assembly language. So when it is converted by an assembly language, the compiler, right, it will try to reorder the code thereby to improve the optimization. So this is what it is. All the hardware resources has to be used efficiently. At the same time, the time, the power, all factors has to be considered. So that's why, right, it will go for reordering. So when it is reordering, this is the constraints that is imposed by the control dependence. So you cannot take the instructions out of that and you cannot move above it. At the same time, right, this is one thing. The second thing is, suppose if the instruction is not control dependent, okay, the instruction is not control dependent on a branch, it cannot be moved, isn't it? So the same thing, if you take this, assume that I have an instruction called K. Okay, so suppose if I have an instruction called K, can I bring it inside this? Can I bring that inside when I'm reordering? Is it right? Some instruction is which is not control of the branch. But if I'm trying to move the branch control, is it a right thing?
No, ma'am.
Okay. So this is also not a correct way. So these are all the two constraints that is imposed by the control dependence. But what generally what is saying is that when you're trying to reorder, right, we can violate the control dependence. Okay, but the thing is, right, this is important. Okay, so the control dependence can be violated, but the correctness of the program should be ensured. So that is very important. Okay. Clear. So we can violate it, but at the same time, right, the correctness of the program has to be ensured. So that is with respect to control dependence. So normally, right, so how do you ensure this program correctness? So actually, it can be ensured by two things. One is the exception behavior. The other one is the data flow. Okay. So see, again I'm insisting data dependence is, control dependent is not a critical property as data dependence. Okay, so when you just go with the data dependence, it's much critical because there is a dependency is much, so it is very critical. But with respect to control dependence, it is not as critical as data dependence. Okay, but something has to be preserved. All the correctness of the program has to get ensured. Okay, so normally, what type of the problem that may exist is one is the exception behavior, another one is the data flow. So, let me see with an example of exception behavior. Suppose we have an example like this. We add some integer addition we are performing. So according to this program, okay, we are trying to add these instructions. Okay, R2, R3, R4. So this is the branch. If it is equal, where it goes, it is go to the else, which means right. If the condition is true, it will goes to else part. If it is false, it will execute this statement. Okay, understood? The add new, so decimal addition, it will add this and store it to the R2. And if we check whether the R2 is equal to 0, when it is equal to 0, the condition is true, it will goes to L1 and it will execute whatever the statement in L1. If it is false, we go first. We'll take the example. Suppose, right, actually this statement is under the control of this branch. Do you agree that? Because based on the test condition only, this is going to get executed. If it is true, it won't. If it is false, this statement is going to get executed. Suppose, for example, I'm just reordering like this. D add you R2, R3, R4. I'm just doing like this. Low R1, I'm just placing the instruction above the branch instructions. Will it be any problem here? Will there be any problem here? We don't think as, you just go with the normal data dependence. So this will be executed because this branch, right, it won't do anything. Nothing is there. Just it will check whether R2 is equal to 0. If it is equal to 0, it will go there. Suppose this case, this condition is clearly forward whether R2 is equal to 0 or not. So we are trying to evaluate this. But we are trying to just swap the instruction before and trying to execute. Unless R2 is not equal to 0, executing this instruction will not matter. Okay, so clearly the statement will get executed. So there won't be any problem with respect to the R2 because this is what we are going to load. So it can be what we are loading it on our own. That is not the problem. Assume when R2 is 0, what going to happen? What will happen? From where it tries to load the data? The memory. So right from 0 somewhere, we are written like assume it is 1 MB memory. So probably right till few this has been reserved for systems. All your BIOS programs, all those things, right? It will be reserved in this address. Interrupt routine, interrupt service routine. I think you know. Have you heard these names and all? ISR interrupts. Have you heard interrupt?
Yes, ma'am.
Yes, ma'am.
In CO or generally interrupt.
Interrupt driven IO.
I'm asking with respect to CO, have you know these words?
Yes, ma'am.
Yeah. Then you know about ISR also.
Yes, ma'am.
Okay. So, normally, right, all those things will be here. So, these are all the predefined things. So, it will be stored somewhere in these addresses. So, we don't have rights to access those places. So, in this case, if suppose if R2 is 0, what we are trying to do, we are trying to load the data from the 0th location to R1. Is it the right thing? Got it or not? We are trying to swap the instruction, not for, for reordering, we are just taking this instruction and we are placing over here. When you are trying to do, it has been done. So until R2 is, until R2 has some value, it won't be a problem. Suppose if R2 is equal to 0, so this case, right, clearly it leads to what? A memory protection error because it will throw some exceptions. So that's what it is they say, exception behavior. So when you are just taking an instruction that is coming under the control of any branch, and if you are trying to move out, unless until if there won't be any exception problem, it is very good. We can proceed it. Suppose if you have an exception problem and it has to get sorted out properly. Okay, this is one scenario. We can violate the control dependence by moving the instruction above. But when you are trying to move that, sometimes right, it may result in program execution, exception behavior error. So we need to handle properly. So this is a one scenario for one example for this. The other example, the another problem is the data flow. Suppose we take an example. We add this is an example. So this case, right, when you check out these cases, here, right, we have add instruction. It is adding this R2 plus R3 and placing the result in R1. Okay. Similarly, right, the same thing. Here R1 is R5 plus R6, and here like R1 is what? R2 plus R3. And you have this instruction R1. Now the question is whether it is going to use the add or it is going to use the subtract. Because both is giving the output. So whether this R1 is depend on add instruction or subtract instructions. So this has to be clear by which one? The branch instructions. Because if the branch is not taken, clear, if the branch, because when the branch is equal to 0, if the R4 is equal to 0, where it is coming to L. So it will comes here. So this is true part. This is the false part. Understood? So if the branch taken, it needs to use the add, isn't it? Else it needs to use the sub. Suppose if I'm trying to replace this instruction here. Yeah, if I'm trying to replace it here, what may be the problem? Will there be a problem here? If I'm trying to replace the sub instruction before the branch instruction. Because the instruction something under the control of branch, I'm just taking out of the order. Will there be any problem? Are you people are there? Will there be any problem?
R1 value will be different now.
Yes, right. It will always use which value?
Sub value.
Sub value, right? If I'm taking the subtraction instruction before the branch instructions, here R1 will always use R1 value will be the subtraction, but it is not the case because the branch is taken, it has to use the add. If the branch is not taken, it has to use the sub. So if suppose if you are trying to reorder, so you may get this problem. So this they are saying it as a data flow. Okay. So this is what the control dependence is. So the thing is, right, nothing is critical. We can do anything. It's not necessary to maintain the order. To maintain the dependencies, but the correctness of the program should be ensured. Okay, so that is very important for the control dependence. So if suppose if you try to violate those things, the problem that may occur is one is the exception behavior you may encounter. The next one is the data flow. Okay, so these two are the major problems with respect to the control dependence. This is all because of what? Because listen, I think I forgot to explain the pipelining with respect to branch. Normally, right, when you just go with the pipelining, you have this, isn't it? Fetch, decode, execute, memory, and write back. So keep remember only at the end of this stage. Yeah, at the end of this stage only you get to know like what is the output of this. Suppose, the previous example, suppose you will take like this. You have like this instruction 1, instruction 2, instruction 3, so and so, something will be there. Okay, at 30, some instruction is there. So this is some position we have this 5. So when the instruction 1 is executing, so after executing branch equals, assume that it is going to 30. So when it is get executed, I told you, right, only during mem at this stage only it get to know output of the branch. So at the 4th clock cycle, only at the 4th clock cycle, instruction 1 we will get to know, right, it needs to go to the 30. So before that 3 clock cycle is there, right? At that time what will happen? The remaining instructions are already loaded. Instruction 2, instruction 3, instruction 4 all will be loaded. So obviously what we need to do, we have to flush the pipeline. Okay, so flush the pipeline. This should be happens. Clear or not? Keep remember instructions. This is for conventional processor. I'm saying when you just go with the conventional processor, with respect to branch instruction, only at the end of this stage you get to know like to where it needs to go. So till then it will start putting the instruction onto this pipeline. So if it is false, no problem. But if something is true, it has to flush it and it has to freshly start the I30 instructions to be loaded. Okay. So to avoid that only, you people have said some solution. What is the solution here?
Branch prediction.
Okay. Just we are going for the branch predictions. So when it is branch prediction, where actually occurs? So you have these two stages: fetch, decode, execute, memory, write back, right? At the decode stage itself, this branch prediction comes into picture. Keep remember this, okay? Decode, while decoding itself, because in the decoder, right, you may have some ALU unit will be there. Inside this decoder, we have some ALU unit. So which is that unit which is responsible to decide where it has to go. Okay, so at the decode itself, we get to know where it has to be done. Suppose if instruction 1 is at decode, by that itself, we get to know where it has to be goes. So only which instruction is loaded, only I2 is loaded. But here, how many instructions has been loaded? How many
Two instructions.
instructions, right? But in this case, only one instruction is. You got it or not? So flushing one instruction is more easy than flushing 3 instructions. So we are thinking like flushing is just removing, but we need to do all the associated things has to be carried out properly. Okay, so that's why like they gone for the branch prediction. Keep remember the branch prediction will happen at the decode stage. It won't goes to execute stage or at the memory stage. At the decode stage itself, the branch predictions will happen. So we will see. After 2 topics, we will have these branch predictions. At the time, we will see something. Okay. I think with that, right, we gone with the basic introductions about the ILP. So ILP, right, just we are going for parallelizing the instructions. So parallelizing is like a basic block. Within basic blocks, we can do it, but if it is between the block, it may be both. So normally, right, when you're trying to achieve parallelism within the instructions, the major problem associated with it is one is the data dependence, another one is the control dependence. And when you go with the data dependence, 2 cases. One is what? True data dependence, another one is the name dependence. So true dependence, the associated hazard is raw hazards. And when you go with the name dependence, you have output dependence and anti-dependence. So in case of output dependence, it is going to be what? Wow, right? Right after right. If it is anti-dependence, it is going to be war hazards. So these things be clear. And the next one is the control dependence. So control dependence, there is no hard and fast rules. The order has to be preserved. But we can do anything, but the correctness of the program has to be ensured. Okay. So the 2 major problems that may arise is one is the exception behavior, another one is the data flow. Okay. So this is all about today's class. Any doubt? So tomorrow you'll see how compiler helps for instruction level parallelisms. Okay, so these are the base problems. So when it is this something has to be sorted out. So we'll see how compiler is helpful for doing instruction level parallelisms. So if you have any doubt, you can ask me. So with the PPT, I'm not comfortable to explain. It's just I feel like as if I'm reading the PPT. So see PPT also there. I will post that and also I will post this. Okay, you just refer whatever you want.